Welcome to Chapter 7. Today is about a problem that looks like it should have a clean answer, and doesn't. We're going to write down 3 definitions of fairness, each one completely reasonable, the kind of thing you'd nod along to in a meeting, and then I'm going to show you that on a single data set you cannot have all 3 at once. So the work isn't picking the fair one, the work is choosing, and then defending the choice. Let's start concrete. You've built a yes or no model. Approve the loan or not, flag the defendant or not, advance the candidate or not. And it runs on a population with 2 groups. You want it to be fair, so you sit down to write what fair actually means. Here's the trap. You'll naturally write 3 requirements, and every one of them sounds exactly like fairness. The bad news, which I'm going to prove to you, is that when the 2 groups have different base rates, and in the real world they almost always do, those 3 requirements fight each other. Now, this isn't a hand-wavy fairness is hard sentiment. It's a theorem, proved independently in 2016 by 2 different groups, Kleinberg, Mullainathan, and Raghavan on one side, and Shuldakova on the other. It says these 3 criteria are mathematically incompatible whenever the base rates differ. It's not a limitation of your tooling, it's not dirty data you can scrub clean, it's structural. And notice what a theorem like this does to you. It doesn't let you dodge the question, it forces you to choose, and choices in engineering have to be defended. So let's meet the 3. This is part 1. I want you to sit with each of these and notice 2 things at once. Each one captures something fairness genuinely seems to require, and yet each is a different statement about your model. First one, demographic parity, sometimes called statistical parity. The thing to hold on to is that this is a statement purely about the model's outputs. It never looks at whether the model was actually right. It just says the model should say yes to the same fraction of Group A as Group B, equal positive rates. Whatever the prediction is, hand it out evenly. Before we move on, let's actually read it. The left side is how often the model says yes to Group A. The right side, how often it says yes to Group B, and the equal sign demands those 2 rates be the same, not close equal. Y hat is the model's prediction, a 1 or a 0. A is the group. Little a and little b are the 2 groups. P just means the probability of. So picture a bank that approves loans at 40% in neighborhood A, but 22% in B. 40 does not equal 22. Parity is violated, and Group B is handed loans far less often regardless of who would actually repay. The value buried in here, outcomes should be equal regardless of base rates. That's demographic parity. Now, back to the 3 definitions. Picture a bank. It approves loans in one neighborhood at 40% and in another at 18%. Demographic parity looks at that and says the loan itself, the thing that buys a house or starts a business, should reach both groups at the same rate, full stop. It deliberately does not ask whether default rates differ between the groups. The claim is about the outcome people actually live with, not about the model's accuracy. Second, equalized odds. This one does look at the truth. It says, among the people who really are positive, the model should catch them at the same rate in both groups. That's equal true positive rates. And among the people who really are negative, it should falsely flag them at the same rate. That's equal false positive rates. So where demographic parity was about outputs, equalized odds is about errors, and specifically about spreading your errors evenly across the groups. Let's read it. The left side is, among the people who truly are positive, how often the model catches Group A. The right side is the same catch rate for Group B, and equalized odds demands they match, plus the identical demand on the false alarm rate among the truly negative. Watch the 2 Y's. Capital Y is the real label. Y hat is the model's guess. Keep them apart. So if a hiring screen advances 90% of the qualified people in Group A but only 70% in B, 90 doesn't equal 70 die violated, and qualified people in B get passed over. The value here, the errors must fall equally. That's equalized odds. Back to the metrics. Here's why that matters. Take a hiring screen that rejects qualified candidates twice as often in one group as the other. 2 people, equally capable, different groups, and one of them is far more likely to be wrongly turned away. That group is quietly absorbing more of the harm the model does when it's wrong. Equalized odds is the criterion that says the cost of your mistakes has to fall evenly. Third, calibration, or predictive parity. This one is about whether the model's probabilities are honest. It says that when the model outputs a number, say 70%, that number has to mean an actual 70% chance, and it has to mean the same thing for everyone, regardless of group. A score is a promise about reality, and calibration is the demand that the promise hold equally for both groups. Read it in words first. The left side is, among everyone the model scored P, how many in Group A actually turn out positive? The right side, the same for B, and both must equal P itself, for every P. P hat is the score the model emits. Little p is a particular score level. The upside down A means for all. So among people scored 0.8, suppose 80% of Group A repay, but only 65% of B, then 0.8 means two different things, and the score is biased. The value here, the number must be equally honest for everyone. That's calibration. Back to the metrics. Think about a doctor reading a hospital's readmission risk score. It says high risk, 0.8, and the doctor acts on it. And crucially, the doctor doesn't know, and shouldn't need to know, which group the patient belongs to. For that to be safe, 0.8 has to mean 0.8 for everybody. The moment the same score means different things for different groups, you've quietly handed the clinician a biased instrument. So, line them up. Demographic parity cares about the visible outputs. Equalized odds cares about who bears the errors. Calibration cares about whether the scores tell the truth. Three different statements, but really, three different values. And I want to be clear, none of these is the obviously correct one. Each is a coherent moral position, and that's exactly what makes the next part uncomfortable. Part 2. I don't want you to take the impossibility on my authority, or even on the authority of a theorem you haven't watched get worked out. So we're going to make it obvious with numbers. Once you see the arithmetic, you can't unsee it. Here's the whole setup, and it really is this simple. Group A has a base rate of 60% truly positive. Group B, 30%. One number, the base rate, does all of the damage, and we'll assume the classifier is calibrated, meaning that among everyone it scores at probability P. The real positive rate is P, honestly, in both groups. Now just watch what that one assumption forces. The quantity to track is positive predictive value, which is just precision. Of the people you flagged positive, how many actually were positive? And here's the key fact. Precision depends on the base rate. Where positives are common, a flag is more likely to be a real one. Where positives are rare, that exact same flag is more likely to be a false alarm, even with an identical model. This one's a definition, so read what it builds. The left side is precision. Of everyone the model flags positive, how many really are? The right side builds that from the base rate and the two error rates, and the thing to notice is the base rate P sitting right on top. So hold the model fixed, same true positive and false positive rates, and just change the base rate from 0.6 to 0.3. Precision falls from about 0.7 to about 0.4. Same model, far less precise where positives are rarer. That's the lever behind the whole impossibility. Back to the arithmetic. The cleanest intuition I know for this is a smoke alarm. One detector, one sensitivity, fixed. Put it in the kitchen, where fires are relatively common, and most of its alarms are real. Take the identical alarm, put it in the bedroom, where fires are rare, and most of its alarms are false. Same device. The trustworthiness of the alarm changed because the base rate changed. Your classifier is that alarm, and your two groups are the two rooms. You can write this down exactly, and Shuldakova did. It falls straight out of Bayes' rule. There's a fixed relationship between precision, the base rate, and your error rates. And once you stare at that relationship, the conclusion is forced. If two groups have different base rates, you cannot keep precision equal and keep your error rates equal at the same time. It's not a modeling choice. It's algebra. There's no threshold, no clever loss function that gets you out of it. This is an identity. It falls out of Bayes and always holds, so read what it forces. The left side is the odds a flagged person truly is positive. That's just precision rewritten. The right side is the base rate odds times the model's hit-to-false ratio. Because the equals sign always holds, if you demand equal precision across two groups with different base rates, the hit-to-false ratio is forced to differ between them. In plain terms, you cannot equalize precision and equalize the error rates at once. That's the algebra under the impossibility theorem. Back to it. Here's the theorem as a picture. 3 corners, the 3 criteria, and you can satisfy any 2 of them. Pick any pair you like, and the third one breaks. Watch it cycle. Keep calibration and equalized odds, parity goes. Keep parity and calibration, the odds go. There is no setting that holds all 3. You are always choosing which one to give up. And this is the same model, just 2 different threshold choices drawn as bars. Move the threshold to satisfy calibration, and the error rates split apart between the groups. Move it to equalize the odds, and the calibration breaks. You're not fixing anything by sliding that threshold. You're only choosing what breaks. The trade-off is a steering wheel, not an escape hatch. Part 3. Let's leave the abstract and go to the most famous time this theorem detonated in public. Broward County, Florida, 2016. A courtroom risk score, and a fight that, underneath all the headlines, was this exact theorem playing out, with real people's freedom on the line. The tool was called Compass, and it fed into bail and sentencing decisions. ProPublica investigated and found that black defendants who were not rearrested had been flagged high risk about twice as often as white defendants who weren't. That's a false positive rate gap, a violation of equalized odds. North Point, the company, fired back. Within any given risk score, the reoffend rate was about the same across groups, so the tool was calibrated. And here's the thing you have to absorb. They were both right. Both pictures were true at the same time. ProPublica's chart showing the error gap, and North Point's chart showing nearly identical reoffend rates within each score. Neither side was lying, neither side was fudging numbers. The disagreement was never about the data. It was about which definition of fairness the tool owed people. That's the theorem, wearing a courtroom's clothes. So here's the lesson of the chapter, and if you take one thing away, take this. Each of these metrics is a coherent value, and none of them is the automatically right one. Which one you owe depends on the deployment, who's using the prediction, what decision they make with it, who pays for the model's mistakes, and whether the base rate difference itself is something you think is just or unjust. The math is settled, the choice is yours, and it is a moral one. Part 4. Everything so far has been about groups, and group fairness has a real blind spot. A model can satisfy demographic parity perfectly and still treat 2 nearly identical people completely differently, as long as the group totals come out even. So let's bring in the older intuition, the Aristotelian one. Similar individuals should be treated similarly. Dwork and colleagues formalized this in 2012 with what's called a Lipschitz condition. In plain words, the difference in how the model treats 2 people can be no larger than how different those 2 people actually are. Close people get close treatment. The model isn't allowed to suddenly swing between 2 applicants who are basically the same. It's a smoothness requirement, placed on fairness itself. This one is an inequality, and the inequality is the whole idea. The left side is how differently the model treats 2 people. The right side is how different those 2 people actually are. And the less than or equal sign says the treatment gap can be no bigger than the person gap. M is the model, big D is distance between its outputs, little d is distance between people. So take 2 applicants with identical finances and different zip codes. If your distance D ignores zip, then D is 0 and the model is forced to treat them identically. But if D counts zip as a real difference, unequal treatment quietly becomes allowed. The value, similar people should be treated similarly, and someone has to define similar. Back to it. 2 loan applicants, identical finances, different zip codes. The whole guarantee now rests on one thing, your similarity metric, the function that decides how different 2 people really are. If that metric ignores zip, the model must treat them alike. But if it encodes zip as a genuine difference, then different treatment becomes permitted, and you've just smuggled structural inequity into the very condition that was supposed to protect against it. The guarantee is only as honest as the distance function underneath it. Now the tempting shortcut. Just delete the sensitive attribute. Drop race, drop gender, and surely the model can't discriminate. This is called fairness through unawareness, and it is intuitive and mathematically weak. The reason is proxies. Zip code, surname, occupation, quietly reconstruct the attribute you deleted. Omit race but keep zip, and the model can still find race. Deleting the column is a documentation choice, not a guarantee. Part 5. Up to now, every metric just reads the data as it sits, but some fairness questions can't be answered from the data alone because you have to distinguish discrimination from a disparity that's actually justified, and those two can produce data that looks identical. To tell them apart, you need a model of how the data was generated in the first place. A correlation between group and prediction can come about 3 different ways. It can be direct, where the group affects the decision straight up. It can be indirect, running through some legitimate mediator. Or it can be spurious, driven by a confounder sitting behind both. Disparate treatment is the direct path, disparate impact is the indirect one, and the right response is completely different for each. The uncomfortable part, your observational metrics can't tell these 3 apart. They see one correlation and conflate all 3 causes. Kuzner and colleagues in 2017 gave us a sharp version of this, called counterfactual fairness. The question it asks is beautifully direct. Would this exact individual have gotten the same decision if they had belonged to a different group, holding everything else about them fixed? That's an intervention, in the due calculus sense, run at the level of a single person. If flipping their group would change the decision, then the model isn't counterfactually fair to them. This reads like a thought experiment. The left side is this exact person's decision in their actual group. The right side is their decision in a world where we flip their group and hold everything else fixed, and the equals sign demands those be the same. The arrow A left arrow A means we intervene and set the group. U is everything personal we hold constant. So take a loan model that only looks at education, but historically, access to that education was shaped by race. Flip the person's race and their credential changes too, so the decision changes. A race-blind model still treats them differently. The value, and it's a strong one, a counterfactual change of group should leave the decision untouched. Back to it. Here's how a model that only looks at education can still encode race. Historical access to education was itself shaped by race, so race flows into the credential, and the credential predicts default. Now run the counterfactual, change this applicant's race, hold everything else fixed, and their credential would change too, because of that historical pathway, so the prediction changes. Counterfactual fairness, violated, even though race was never an input. The remedy is to exclude variables that sit downstream of group along an illegitimate path. Part 6. Every metric so far hands you a verdict, fair or not fair, a gap or no gap. But sometimes you want a dial, not a verdict. How much unfairness is there, and where is it coming from? For that, we borrow a tool from economics, the same family of indices used to measure income inequality. It's called the Generalized Entropy Index. The idea, give each individual a benefit, essentially how well the model treated them relative to what they deserved, and then measure how unequally that benefit is distributed across everyone, exactly the way economists measure how unequally income is spread. There's a parameter, alpha, that recovers specific famous indices: mean log deviation at 0, the tile index at 1, and at 2, something close to the squared coefficient of variation, which is a common default. Don't let the formula scare you. Read what it does. The left side is a single number for total unfairness. The right side measures how spread out each person's benefit is around the average, straight from income inequality economics. Little bi is each person's benefit, mu is the average, and the one to watch is alpha, the exponent. Alpha is a knob. Take the same spread of benefit and read it at alpha equals 0 versus alpha equals 2. A low alpha makes the index scream about the worst served at the bottom. A high alpha responds more to the top. So picking alpha is itself a value choice about whose harm the number cares about most. That's the entropy index. Back to it. That alpha isn't a technicality, it's a values knob. A low alpha makes the index scream about the worst served people, the bottom of the distribution. A high alpha makes it more responsive to the top. Same distribution of benefit, different alpha, different number, because you are choosing whose harm you most want the metric to notice. Picking alpha is itself a moral decision about who you're trying to protect. And here's its best trick. The total unfairness splits cleanly into two pieces, the part that lives between groups and the part that lives within them. A standard group audit only ever sees the between group term. It's completely blind to inequity happening inside a group, and the ratio of those two pieces actually points you toward the remedy, whether your problem is across groups or hiding inside one. Part 7, and this is where the whole chapter comes to rest. Everything I've handed you so far is machinery, and machinery is seductive because it feels like an answer. But notice what it actually does and doesn't do for you. It can carry out a decision you've already made. It cannot make that decision, and it won't stand up and justify it when someone asks you why. That justification, written down and owned by you, is the real thing you ship, not the metric. The argument for the metric. Quick tour of what you can actually reach for. 3 families. Pre-processing. Reweight or resample the training data before you fit. Model agnostic and upstream. But it can't fix truth that was misrecorded. In processing. Bake fairness into the objective as a constraint while training. Post-processing. Adjust the outputs or thresholds after the fact. All useful, but notice none of them resolves the impossibility theorem. They implement a choice within it, and none of them reaches the upstream structural bias that produced the data in the first place. So here's the form your work should take, every single time. 6 boxes. Specify the metric you're choosing. Compute it. Name the conflict. Say out loud which criterion you're giving up. State your choice. Defend it in writing, tied to the deployment. And, the box people love to skip, name what would change your mind. If you can fill these 6 honestly, you've done fairness engineering. If you can't, you've just computed a number. Let me be honest about the ceiling. Group metrics can't certify that 2 similar individuals were treated consistently. Individual fairness needs a similarity metric that someone has to load with values. Causal fairness needs a structural model the data simply can't give you. Each approach needs something the others can't supply, and not one of them can tell you whether the prediction task itself was even fair to pose in the first place. The tools have a hard edge, and you should know exactly where it is. So, the supervisory move, the thing I want you walking out with. Understand the math, choose the values, and defend the integration. 3 formally distinct metrics can be flatly incompatible on a single dataset the moment base rates differ. That's structural, and it isn't going away. What's yours to own is connecting the metric you chose to the deployment and to the people who bear the cost of being wrong. Next time, we turn from fairness to a different kind of pressure on your model, adversarial robustness.